Hello, everyone. Welcome back. Today, I'm going to be talking about evaluating logarithms. So, we already did a few classes ago. We already talked about kind of an introduction to logarithms and what logarithms are in general. But just a quick reminder on that logarithms are a different way of writing our exponentials. Right? Logarithms are where the unknown is the exponent, right? And so it's swapped around. Or in other words, it's like the inverse, right? It's the inverse of our exponential equation. I think they even give us an example here, and they say that the logarithmic function for every exponential function y equals a to the power of x, the inverse equation is x equals a to the power of y, right? Because for inverse, as we know, we swap x and y in order to find the inverse of anything in general, right? That's just a general thing we do. Okay. And then over here it says the inverse equation can be written as y equals log with the base a to the power, a with the base a of x, right? And so basically the logarithmic function is, long story short, it's the, what's it called? It's the inverse. It's the inverse of the exponential function. So just given what we know about inverses already and that sort of thing, that tells us a lot about what we would need to know for this. So here we go. I'm going to draw both the regular exponential on my graph and then also the logarithmic form. So if we have something like y equals 2 to the power of x, well, what does that look like? Well, if x is 0, y is 1, then we have a half, a quarter, and so on. What about 1? 2 to the power of 1 is equal to 1, or sorry, is equal to 2. 2 to the power of 2 is equal to 4. And then 2 to the power of 3 is equal to 4, 5, 6, 7, 8, like that. So let's connect those dots. And there we go. Okay, so what would the inverse of that look like? Basically, we swap our x's and our y's, right? We're going to reflect through the y equals x axis like this in order to get it. Hmm. And we're going to get something that looks like this. Okay, and I'm going to erase this because this kind of makes it look like it's an asymptote, and this is not an asymptote. It was just me kind of trying to visualize what was what in order to get this one, which is y equals log with a base 2 of x, like that. Awesome. Okay. Okay, so let's express all of these in logarithmic form, okay? So how will we express 7 squared equals 49 in logarithmic form? Well, that's when we have log with a base 7 to the power of 2 equals 49, right? What about this one? Log with what's the base? 5 to the power of, right? The answers are power, right? Power of 3 is 125, so we write it like that. And then last but not least, log with the base 2 to the power of 5 is equal to 32. So we write it like that. Awesome. Okay. How about example 2? Here it says, express each of these in exponential form. Okay, so in this case, we're going to do the opposite. Okay, so for this one, we have base is 2, so 2 to the power of the answer, which is 4, equals to 16. For this one, we have 3 to the power of 4 is equal to 81. And then for this one, 6 to the power of 2 equals to 36. All right, and next I have us actually go on and evaluate these logarithms. So let's do that as well. This one is log 4 something 16. So the question we got to ask ourselves is 4 to the power of what is 16? Well, 4 to the power of 2 is 16, so the answer is 2. For this one, log with the base 5 of 625, that means 5 to the power of what is 625? Well, 5 to the power of 4 is 625, so our answer is 4. And then for this one, log with the base 4 to the power of what is 64? Well, 4 cubed, or 4 to the power of 3, is 64. So there we go. Okay, let's move on to the next page for some more. Here it says solve for x. In this case, they want to know 8 to the power of 2 is equal to what? Well, 64. So x would be 64. Okay. Next one is b. 2 to the power of what is 1 over 64? Well, we know x has got to be negative something, right? Because it flipped, right, to negative to the reciprocal. And so now that we've taken care of the reciprocal part, 2 to the power of what is 64? Well, 2 to the power of 6, I believe, is 64. Yes, it would be power of 6. So therefore, to get to negative 60, or sorry, to get to 1 over 64, it would need to be negative 6, right? 2 to the power of negative 6 is 1 over 64. Okay? And that's another step we could write. We could say 2 to the power of x is 1 over 64, if that does help us at all. All right, this one says log x equals 3. And keep in mind, whenever there's no base, that means there's a base of 10. So what they're really asking is 10 to the power of 3 equals what? Well, x is going to be equal to 10 to the power of 3, which is 1,000. And so our answer here is 1,000. Awesome. Okay, this one here says to estimate the value of the following. So I'm going to talk about how we're going to do that. Okay, so for this one here, it says log 40 base 4, 45. And the reason they're saying to estimate the value is because there's not actually going to be whole numbers values for this, right? Like 4 to the power of 2 is 16, and 4 to the power of 3 is 64. And so it's going to be something between 2 and 3, but it's not going to be an easy whole number solution here for these ones. So what we're going to do in order to estimate the value is we're going to use this rule that says that we can rewrite this as log 45 over log 4. Okay, and now you're going to grab your calculator and type into your calculator log 45 divided by log 4 and press enter and see what you get. And you should probably get something like 2.75 approximately. It'll be a long decimal. It won't just end there, but you can just round to a decimal point or two. Okay, let's try the same thing for this one. Here we have log with the base 5, 100. So this is going to be log 100 over log 5. Now log 100 we know is 2, right? Because, and how do we know that? Well, 10 to the power of 2 is 100, right? So this is just going to be 2 over log 5. And let's punch that in our calculator. 2 divided by log 5 is going to give us 2.86 approximately. Good. All right, what about this one? Log with a base 3, 81 times 3. Well, here's the thing about this one. This one actually we don't necessarily need to estimate the value because we can find the exact value. 3 to the power of what is equal to 81? Well, let's think about it. 3 to the power of 4 is 81, right? And so the answer for this one would be just 3 times log with a base 3 of 81, which we said was 4 because 3 to the power of 4 is 81. So that's just going to be 12. So this one we don't actually have to estimate. Oh, wait. I think this log, isn't multiplied here. It's the power. It's 3 to the power of 3 log 81. Okay, so 3 to the power of 4 then, because log with the base 3 of 81 is going to be 4, right? Because 3 to the power of 4 is 81. So then that would mean this is also 81. That also makes sense because here we have 3 and then to the power of log 3, which kind of, those things kind of cancel if we think about it, right? It's we're putting a log as an exponent. Okay. Let's try this last example here when it comes to just evaluating logarithms and understanding them. So this one says that the Richter scale is used for measuring the magnitude of an earthquake. The Richter scale magnitude is given by R equals 0.67 log of 0.37 E plus 1.46, where E is the energy in kilowatt hours released by an earthquake. An earthquake releases 15.5, looks like billion, billion kilowatt hours of energy. What is the earthquake's magnitude? Okay, so it already told us that the magnitude is given by R, right? So if we want to know what's the earthquake's magnitude, we've just got to plug in. All we need to do here is we need to plug in 15.5 billion for E, right? Because here they gave us the number of kilowatt hours, they gave us the energy, they just want R to find out what this is on the Richter scale, to find out the magnitude. So let's do that. R is equal to 0.67 log of 0.37 times 15,500 plus 1.46, like that. And that's going to be equal to 0.67 times, let's find out what that is. It's going to be about 9.76 plus 1.46, which brings us to about 8. So this is going to have a Richard scale of 8. Okay. Then B asks, how many kilowatt hours of energy would an earthquake have to release in order to be a 6.5 on the Richard scale? Okay, so in this case, we're going to need to use logarithms, right? Because they're asking the opposite question. Previously, to learning about logarithms, I would have just said, oh, just use trial and error once you get to the last step and give us an approximation. In this case, we can actually solve directly using logarithms, using that function on our calculators. So let's do that. This time, 6.5 is going to be the answer. And we want to find out what E, how many kilowatt hours would we get for doing this? 0.37 E plus 1.46, like that. Okay, so that means 5.04 is equal to 0.67 log 0.37 E, like that. Okay, then that means 7.52 equals log 0.37 E. Okay. And that means what? That means 10 to the power of 7.52 is equal to log 10 to the power of 7.52 is equal to 0.37 E. And then we're going to divide to figure out E. So E is going to be 10 to the power of 7.52 over 0.37. So that's going to end up being, let's see. Ooh, that's a big number. 897.7 kilowatt hours. Awesome. So yeah, 89,494,897.7 kilowatt hours. And so there we go. There's our answer. All right, well, that is it for evaluating logarithms today. Next time, we'll talk about the laws of logarithms. Have a great rest of your day, everyone, and I will see you for then. Bye, everyone.